What if you could step onto a world where time itself stands still, where a single heartbeat stretches out into epochs, and the rise and fall of civilizations back on Earth would pass in less time than it takes to draw a breath? We're venturing into one of the most extraordinary ideas in all of cosmic science, the concept of frozen time planets, places where 1 second of your experience would equal 1,000,000 years everywhere else. This isn't science fiction. It's a staggering possibility rooted in the real physics of our universe, a glimpse into how time and gravity intertwine in ways that completely upend our everyday understanding of reality. Think about that for a moment. On a planet like this, the mountain ranges wouldn't erode, the stars overhead wouldn't seem to move, a falling drop of water might take centuries to hit the ground. You could watch entire species evolve in what feels like an afternoon, or witness the slow dance of galaxies shifting in the sky, all while the universe outside carries on at its frantic, familiar pace. It's almost impossible to wrap our minds around, and that's exactly what makes this idea so compelling. It challenges us, it stretches our imagination to its outermost limits, and asks us to reconsider everything we assume about existence. Throughout human history, we've looked up at the night sky and wondered what secrets lay hidden in the depths of space. We've built stories, crafted myths, and developed entire fields of science to make sense of the cosmos. But some concepts are so strange, so beautifully counterintuitive, that they feel less like answers and more like invitations to wonder, to explore, and to marvel. That's the journey we're beginning today. We're going to venture into the science and the stories behind these frozen time worlds. We'll explore how such places could exist, what it might be like to stand on one, and why understanding them doesn't just teach us about the universe, it teaches us about ourselves, our place in time, and the astonishing possibilities that wait, silent and patient, in the far reaches of space. So settle in, let's begin. To truly grasp the nature of these frozen time planets, we have to move beyond our everyday experience. We live our lives governed by a steady, reliable tick of the clock, a rhythm that seems universal. But Einstein's revolutionary theory of general relativity shattered that notion. It revealed that time is not a fixed, absolute backdrop for the universe. Instead, it's a fluid, malleable dimension that is intimately woven together with space and, most importantly, gravity. The stronger the gravitational pull you experience, the slower time passes for you relative to someone in a weaker gravitational field. Now, imagine a planet with a gravitational force so unimaginably powerful that this time-slowing effect is pushed to its absolute extreme. This is the heart of a frozen time world. We're not talking about the gentle pull of Earth's gravity, which slows time just enough that our GPS satellites need constant corrections to stay accurate. We're talking about a planet orbiting something with the mass of a giant star, or even more incredibly, a black hole. In such an environment, the gravitational field would be so intense that time itself would be stretched and warped. A single second for an observer on that planet's surface could equate to millennia, or even millions of years, for everyone else in the universe. This isn't a flight of fantasy. It's a direct prediction of our most rigorously tested and confirmed scientific theory. The equations of general relativity allow for this possibility, painting a picture of a cosmos where the flow of time is a local phenomenon, not a universal constant. A traveler stepping onto such a world would, from our perspective, appear to move in super slow motion. Their every action, every thought would be drawn out across the ages. Meanwhile, from their perspective, looking out at the stars, the universe would be a frenetic blur of motion, with galaxies swirling and stars being born and dying in the blink of an eye. The conditions required for such a planet are, of course, beyond extreme. It would need to orbit perilously close to an incredibly dense and massive object, likely in the final, violent stages of its life cycle. The environment would be hostile in ways we can scarcely comprehend. bathed in intense radiation and subject to titanic tidal forces. And yet, the mere possibility that the laws of physics permit such a reality opens a door to a universe far stranger and more wonderful than any fiction. It shows us that the cosmos operates on a set of rules that can produce phenomena which challenge the very foundations of our perception. So how does this incredible warping of time actually work? The key lies in Einstein's field equations, the mathematical heart of general relativity. These incredibly complex formulas describe how mass and energy tell spacetime how to curve, and how that curved spacetime in turn tells matter and light how to move. It's this curvature that we experience as gravity. The deeper you are within a gravitational well like that of a planet or a star, the more spacetime is curved, and the slower time flows relative to an observer far away in flat, undisturbed space. We can actually quantify this mind-bending effect with a specific formula derived from those equations. For the time dilation caused by gravity, physicists use what's known as the gravitational time dilation formula. It tells us that the closer a clock is to a source of gravitation, the slower it will tick compared to a clock that's farther away. The effect is minuscule for most objects we encounter. For example, a clock on the surface of the Earth will run very slightly slower than a clock on a satellite in orbit. This tiny difference is so real that our global positioning system has to account for it. If it didn't, your phone's map would be off by several miles within just a few hours. But the formula also reveals that this effect isn't linear. It becomes exponentially more dramatic as you approach an object of extreme density. This is where supermassive black holes enter the story. A black hole is a region of spacetime where gravity is so intense that not even light can escape its pull. The point of no return is called the event horizon. As you approach this boundary, the equations predict that time dilation would skyrocket towards infinity. From the perspective of a distant observer, a clock falling towards a black hole would appear to tick slower and slower, freezing completely at the very edge of the event horizon. For an intrepid astronaut on a planet orbiting just outside that horizon, a single second of their local time could equate to millennia or even eons for everyone else in the universe. It's crucial to understand that this isn't just an optical illusion or a trick of perception. It is a fundamental difference in the actual passage of time. The fabric of reality itself is being stretched. Another pathway to extreme time dilation, though less relevant for a stationary planet, is velocity. According to special relativity, as an object approaches the speed of light, time for that object slows down relative to a stationary observer. Combine these two effects, immense gravity and immense speed, near the accretion disk of a black hole, and you have a recipe for the most extreme time warps the universe could possibly allow. While the environments around black holes present the most plausible natural setting for such dramatic effects, theoretical physics also explores other possibilities. Some models of exotic matter, like the theoretical matter needed to stabilize a traversable wormhole, suggest configurations that could manipulate spacetime in equally radical ways. Though purely speculative, these ideas push the boundaries of our understanding, suggesting that the universe's deepest laws might one day allow us to engineer such profound experiences of time, turning the most far-fetched science fiction into a distant, tantalizing possibility. Of all the cosmic objects that warp the fabric of spacetime, none do so more violently and completely than the black hole. These gravitational behemoths are the ultimate engines of time distortion, creating environments so extreme that the very concept of a universal clock breaks down entirely. While any massive object can slow time, a supermassive black hole elevates this effect from a curious anomaly to a dominant, overwhelming force of nature. At the heart of a black hole's power is its unimaginable density. A typical supermassive black hole, like the one at the center of our own Milky Way galaxy, can contain the mass of millions or even billions of suns, all crushed into a region of space smaller than our solar system. This concentration of mass creates a gravitational pull so ferocious that it warps the surrounding spacetime into a deep, bottomless well. The steeper the sides of this well, the more dramatically time is stretched for anything caught within its grip. The most critical boundary around a black hole is its event horizon, the famous point of no return. For a distant observer watching something fall toward a black hole, its approach to the event horizon would be a spectacle of seemingly frozen time. A clock on the falling object would appear to tick slower and slower, its light becoming redder and dimmer until it finally seems to stop completely, forever etched onto the edge of the horizon. Nothing, not even information, can escape from beyond this point to update us on what happens next. From our perspective in the outside universe, time for that object has effectively ceased to flow. Now envision a planet somehow surviving in a stable orbit just outside this event horizon. This would be a world perpetually skirting the ultimate abyss, held in place by a delicate balance between the black hole's immense gravity and the planet's orbital velocity. For any being standing on the surface of this world, local time would feel perfectly normal. Their heart would beat at a regular rhythm, and a dropped object would fall to the ground in a familiar second. But their view of the universe beyond their own sky would be a frenzied, high-speed light show. The light from distant stars, blue-shifted by their incredible orbital speed, would streak across the heavens. Entire galaxies would spin, evolve, and fade in the time it takes them to finish a single sentence. A conversation begun on this planet's surface would, by the time it concluded, have spanned the rise and fall of civilizations across the cosmos. The conditions on such a world are beyond hostile, they are apocalyptic. It would likely be bathed in intense, lethal radiation from the superheated material of the accretion disk swirling around the black hole. The tidal forces from the black hole's gravity would be monstrous, potentially stretching and composing the planet itself in a constant tectonic agony. And yet, the sheer physics of the situation allows for the possibility. It stands as one of the universe's most profound demonstrations of relativity, a place where time itself is not a constant river but a fluid that flows at different rates, dictated entirely by the curvature of space. While black holes offer a natural, if terrifying, pathway to frozen time, theoretical physics opens a door to possibilities that are even more staggering. The prospect that such extreme environments might not just be found but could actually be built. This brings us to the edge of known science, to concepts like negative energy and cosmic strings, where the universe's deepest laws might allow for the engineering of reality itself. To grasp this, we first have to understand a peculiar prediction of quantum field theory, negative energy densities, often referred to as exotic matter. This isn't antimatter. Antimatter has positive energy and gravitates normally. Exotic matter would have a kind of negative energy, and according to general relativity, this would produce a gravitational repulsion instead of an attraction. It's a bizarre substance that, while never observed in bulk, is permitted in tiny quantities by the laws of quantum mechanics as a fluctuation in the vacuum of space. Think of the fabric of spacetime as a simmering sea of virtual particles popping in and out of existence. For an infinitesimally brief moment, a region of space could exhibit these negative energy properties. Now, imagine if a supremely advanced civilization could find a way to produce and stabilize significant quantities of this exotic matter. One of the most compelling theoretical applications is the stabilization of a traversable wormhole. A wormhole is like a cosmic shortcut, a tunnel through the folded fabric of spacetime connecting two distant points. But according to standard general relativity, such a tunnel would collapse instantly into a black hole. The only way to prop it open, to make it traversable, would be to line its throat with this exotic matter, whose repulsive gravity would counteract the natural tendency to collapse. Here's where time dilation enters the picture. The intense gravitational fields at the mouths of a stabilized wormhole could create dramatic time-shifting effects. If one mouth were moved relative to the other or placed in a powerful gravitational field, a clock next to one end could tick at a radically different rate than a clock at the other. And travelers stepping through could emerge not just in a different location, but in a different epoch entirely. This isn't just transportation. It's a form of time travel engineered through the meticulous manipulation of spacetime's fundamental properties. Another theoretical construct that could warp time on a grand scale is the cosmic string. These are not strings in the everyday sense, but hypothetical, infinitely long one-dimensional defects in the fabric of spacetime, remnants from the universe's earliest, most violent moments of creation. A cosmic string would be narrower than a proton but possess unimaginable density, with the mass of an entire star compressed into every mile of its length. The spacetime around such an object would be severely distorted, not in a spherical way like a planet or star, but in a sharp, conical manner. If two cosmic strings were to move past each other at high speed, the geometry of spacetime between them could become so twisted that closed time-like curves might form, paths through spacetime that loop back on themselves, effectively allowing for travel into the past. While the time dilation effects here are more about time travel than frozen moments, the principle is the same. The underlying structure of reality is being bent and folded to alter the flow of time itself. A civilization that could somehow harness or create cosmic strings would be wielding power over the chronometric architecture of the cosmos. The common thread in these speculative ideas is the move from finding extreme environments to creating them. It shifts the question from what does nature allow to what could intelligence build. This is a theme that moves beyond established astrophysics into the realm of futurism and cosmology, pondering the potential end goals of a civilization that has mastered the laws of physics. Would such a society use this knowledge to create archives where information is stored for eternity, a single second within preserving the entire history of a culture? Or perhaps they would construct sanctuaries where one could experience the slow, deep time of the universe firsthand, watching galaxies evolve from birth to death as if observing the growth of a forest. These concepts, while firmly in the domain of theory and speculation, are not mere fantasy. They are rigorous mathematical explorations of the boundaries of our physical theories. They show us that the universe might be far more malleable than we ever dreamed, and that time, the most relentless and universal force in our human experience, could someday become a medium for engineering and art. So far, we've explored how immense gravity, particularly around a black hole, can stretch a single second into an eon. But gravity is only one of the two great forces that can warp time according to Einstein's theories. To fully appreciate why a frozen time planet is a uniquely gravitational phenomenon, we need to understand its counterpart, time dilation from velocity. The key difference between these two effects lies in their very nature and the experience of the traveler. Velocity time dilation, governed by Einstein's special theory of relativity, states that the faster you move through space, the slower you move through time relative to a stationary observer. It's a universal speed limit trade-off. As your velocity approaches the speed of light, your personal time grinds nearly to a halt from the perspective of the rest of the universe. This isn't just theoretical, we observe it constantly. Particles in giant accelerators like the Large Hadron Collider are boosted to fantastic speeds, and their decay rates slow down dramatically, proving that their internal clocks are running slower than the clocks in the lab. Now imagine a futuristic spaceship designed not for exploration, but for time travel. This vessel accelerates relentlessly, using some impossibly efficient engine to reach 99.99% of the speed of light. For the brave astronaut on board, life continues as normal. They might brew a cup of coffee, read a book, or take a nap, with each action taking its familiar, comfortable amount of their own time. But when they finally slowed down and returned to Earth, they'd confront a staggering reality. While perhaps only a few years passed for them, centuries or millennia have swept across their home planet. This is velocity-based time dilation in its most dramatic form. However, this scenario creates a profoundly unstable and fleeting kind of frozen time. The astronauts' slowed clock is entirely dependent on their incredible motion. The moment they fire their engines to decelerate, to turn around, or to change course, that velocity-based time dilation effect begins to diminish. Their experience of time would gradually resynchronize with the universe's. There is no lasting, stable environment here. It's a temporary state confined entirely to the journey of a single object in motion. You couldn't build a civilization or even stand on a planet that experiences this kind of time dilation, because the planet itself would have to be in this incredible, unstoppable motion. This is where gravitational time dilation reveals its unique and profound advantage for creating a permanent frozen time world. Unlike velocity, gravity's effect on time is tied to a location in space, not the state of motion of an object. A planet orbiting just outside the event horizon of a black hole is caught in a specific, incredibly curved region of spacetime. This curvature is a fixed feature of that cosmic geography. Any clock placed on that planet's surface will tick at the same incredibly slow rate relative to the wider universe, regardless of what that clock is doing. Whether it's sitting on the ground being carried by a creature or launched on a local rocket, the immense gravitational potential at that location ensures that time flows at one universally slowed pace for everything there. Think of it like this: velocity time dilation is like driving a car incredibly fast down a straight highway. Your speed relative to the road changes your experience. But the moment you hit the brakes, that relationship ends. Gravitational time dilation, on the other hand, is like being parked at the very bottom of an impossibly deep and steep valley. The valley itself defines your experience. You could be asleep in your car, walking around outside it, or having a picnic. Your location at the bottom of that gravitational well is what dictates the slow passage of time. It is a persistent environmental condition. This stability is what makes the concept of a frozen time planet not just a thought experiment, but a theoretically valid, permanent feature that could exist in the cosmos. It would be a world where the mountains, the oceans, the atmosphere, and any potential life would all share the same radically slowed temporal rhythm. From our distant perspective, their entire world would be a still life painting, a single moment drawn out across the lifetime of stars. The relentless, stable pull of gravity provides the anchor that mere velocity cannot, offering a glimpse into a universe where time itself is not a river, but a landscape with mountains and valleys of its own making. For decades, the mind-bending predictions of general relativity existed primarily as elegant mathematics on a page, confirmed by small-scale tests, but untested in the most extreme environments imaginable. That all changed with one of the most monumental achievements in the history of astronomy: the Event Horizon Telescope's capture of the first ever image of a black hole. This wasn't just a picture, it was a direct window into the most violently distorted region of spacetime ever observed, offering us stunning, real-world evidence of the very effects that could create a frozen time planet. The primary target was M87, the supermassive black hole at the heart of the Messier 87 galaxy. To grasp the scale of this endeavor, consider that observing M87 from Earth is akin to trying to read the date on a coin in Los Angeles while standing in New York City. This impossible feat was accomplished by linking radio telescopes across the globe, creating a virtual observatory the size of Earth itself. After years of data collection and analysis, the world was presented with an image that instantly became iconic: a brilliant, fiery ring of light surrounding a dark, central shadow. That glowing ring is the black hole's accretion disk, a maelstrom of superheated gas and dust spiraling inward at nearly the speed of light. The central darkness is the black hole's shadow, a region twice the size of the event horizon where light is bent so severely that it cannot escape, giving us our first direct glimpse of the gravitational abyss itself. This image is more than a silhouette. It's a detailed map of extreme physics in action, and it provides clear observational clues about time dilation. The light we see coming from that bright ring is produced by matter screaming along in its final orbits, but the light from the side of the disk that is rotating toward us is dramatically brightened and blue-shifted, while the light from the side rotating away is dimmed and redshifted. This is a direct result of the combination of its orbital velocity, a significant fraction of light speed, and the incredible gravitational field it's racing through. The photons fighting their way out of that deep gravitational well lose energy, their wavelengths stretched toward the red end of the spectrum. For matter deep within that well, time is crawling. Now let's take this a step further and imagine we could see a clock falling into that disk. From our safe, distant vantage point, that clock would appear to tick slower and slower as it approached the event horizon. Its light would redden and fade until it seemed to freeze completely, its final tick stretched out across eternity. The HD image doesn't show a single clock, of course, but it captures the integrated light from entire regions where time is flowing at radically different rates. The severe distortion and asymmetry of the ring are the fingerprint of relativity itself, a signature that the equations of Einstein are not just abstract theory, but the actual operating manual for the most powerful engines in the universe. More recently, the Event Horizon Telescope collaboration turned its gaze inward to the heart of our own Milky Way galaxy and captured an image of Sagittarius A. This presented a different kind of challenge and revelation. While M87 is a behemoth, SGR is like a quick, skittish shadow. It has a much smaller event horizon, and matter orbits it in a matter of minutes rather than days, meaning the brightness and pattern of its accretion disk change incredibly rapidly. Piecing together a clear image was like trying to photograph a puppy running in circles using a camera with a very long exposure time. The success in imaging SGRA and confirming it also possesses that telltale dark shadow surrounded by a fiery ring was a crucial confirmation. It demonstrated that the physics of general relativity holds true for black holes of vastly different scales and environments. Observing these two different monsters allows scientists to stress test relativity in new ways, probing the nuances of how spacetime behaves under conditions that can never be recreated in a laboratory. Each observation adds another data point, another validation that the incredible time-warping effects we've been discussing are not just mathematical possibilities, they are active, measurable phenomena shaping the real cosmos. These revelations from the Event Horizon Telescope have done something profound. They have begun to bridge the gap between theoretical prediction and observational reality. They show us that the environments where time itself is stretched to its breaking point are not just science fiction, they are out there, and we now have the technology to study them. Every new observation peels back another layer, bringing us closer to understanding what it truly means to exist on the edge of eternity, where a single second can hold the weight of 1,000,000 years. Considering the unimaginable forces at work around a black hole, the very idea of a planet forming there seems to defy all logic. The standard story of planetary formation is a gentle, gradual process. A new star forms from a collapsing cloud of gas and dust, and the leftover material in the circumstellar disk slowly clumps together, eventually building planets over millions of years. It's a serene, almost peaceful image of cosmic construction, but near a supermassive black hole, the environment is anything but serene. It's a chaotic, violent maelstrom where the rules of physics are pushed to their absolute limit. So how could a world possibly coalesce in such a destructive place? The answer likely lies not in the standard model, but in a far more extreme and rapid process. Instead of a calm protoplanetary disk, imagine a vast, swirling torrent of material, the black hole's accretion disk. This is a seething ocean of gas, dust, and shattered celestial bodies, all superheated to millions of degrees and whipped around at relativistic speeds by the black hole's irresistible gravity. Within this chaotic flow, density waves and shock fronts could create temporary pockets of stability, regions where material is compressed with immense force. In these violent nurseries, a planet might not form through slow accretion, but through a form of gravitational collapse so rapid it's more like a cosmic avalanche. A passing star torn apart by tidal forces could provide a sudden, massive infusion of heavy elements, creating a dense knot of matter. If this knot has enough mass and angular momentum, it could theoretically resist being pulled apart long enough to collapse directly into a planetary body under its own weight. It would be a world born from catastrophe, forged in an instant from the shredded remains of other stars, a diamond created under the most extreme pressure imaginable. But formation is only half the battle. Survival is the true test. For this planet to become a stable home for extreme time dilation, it must achieve a perfect and precarious balance. It needs to find an orbit just outside the event horizon where its orbital velocity precisely counteracts the black hole's gravitational pull, preventing it from either spiraling inward to its doom or being flung out into the wider galaxy. This stable orbit is known as the Innermost Stable Circular Orbit, or ISCO. For a non-rotating black hole, this orbit is 3 times the radius of the event horizon. For a rapidly spinning Kerr black hole, this orbit can be brought even closer to the point of no return. A planet locked in this orbital dance would be utterly unlike any world in our solar system. The shear forces involved would likely create a world of extremes. Its surface might be a smooth, featureless plane of super-dense, degenerate matter, compressed by the incredible gravity and polished by a constant sandblasting of high-energy particles. There would be no mountains or valleys. Any topographical feature would be crushed flat or eroded away instantly on a geological timescale. Its atmosphere, if it could even hold onto one against the black hole's pull and the radiation from the accretion disk, would be a bizarre metallic vapor, perhaps a shroud of iron and other heavy elements boiled off its own surface. The energy sources for this world would be utterly alien. There would be no sun in the sky, only the terrifying, dark silhouette of the black hole's shadow, encircled by the blinding, frenetic light of the accretion disk. The primary heat would come from within, generated by the intense tidal forces flexing the planet's core, a process similar to what heats the moons of Jupiter, but magnified to an apocalyptic degree. The planet's surface could be a global ocean of molten rock, constantly churned by the gravitational stresses, making it a world of perpetual, violent geology. This isn't a place for life as we know it. It's a monument to gravitational physics, a testament to the fact that planets can exist in forms and places we are only beginning to dare imagine. Yet for all the compelling theory, a critical question remains. Could such a world actually exist out there in the cosmos? And if so, how would we ever find it? The search for these ultimate time-warped planets is one of the most fascinating and difficult challenges in modern astronomy, pushing our technology and our ingenuity to their absolute limits. Astronomers aren't simply pointing telescopes at random black holes hoping to get lucky. They are developing sophisticated methods to detect the faint, telltale signatures that would betray the presence of a planet dancing on the edge of oblivion. The first and most obvious challenge is the sheer distance and scale involved. The nearest supermassive black hole, Sagittarius, at the center of our galaxy, is 26,000 light-years away. Resolving a planet orbiting it would be like trying to spot a single firefly circling a dim lighthouse lens from across an entire ocean. The blinding glare from the hot, swirling gas of the accretion disk would easily overwhelm the faint reflected light of any potential world. So, astronomers must rely on indirect methods, on reading the subtle clues written in the light and motion of these extreme environments. One of the most promising techniques involves studying the gravitational influence such a planet would have on the inner edge of the accretion disk itself. The disk isn't a perfectly smooth, uniform structure. It has clumps and ripples. A massive, close-orbiting planet would create a consistent gravitational tug, potentially clearing a small gap in the disk or creating a regular, repeating pattern of density waves. By meticulously analyzing the light output from the disk over long periods, scientists could potentially detect the periodic dimming or specific frequency shifts caused by this unseen gravitational shepherd. It would be like listening to the hum of a powerful engine and hearing the faint, regular click of a single tiny gear within the machinery. Another powerful tool is the phenomenon of gravitational microlensing. This occurs when the gravitational field of a foreground object, like a star or a black hole, acts as a lens magnifying the light of a more distant star behind it. If a planet is orbiting that foreground object, it can create a secondary, telltale blip in the magnification curve, a brief, additional brightening within the larger lensing event. While typically used to find planets around distant stars, this method could, in theory, be applied to black holes. A microlensing event caused by a black hole would be exceptionally rare and long-lasting, and a perturbation from an orbiting planet would provide a unique signature, a tiny wobble in the lens's focus revealing the hidden world. Future missions are being designed with the sensitivity to hunt for these exact kinds of signals. The upcoming Nancy Grace Roman Space Telescope, for instance, will conduct vast microlensing surveys of the galactic bulge, monitoring millions of stars to catch these rare cosmic alignments. While its primary goal is finding more common exoplanets, its data could be sifted for the anomalous, ultra-long duration events that might point to a black hole lens and any strange planetary bumps in the data. Even more advanced concepts, like a proposed spacecraft using the sun's gravity as a giant lens, could one day provide resolution powerful enough to directly image the regions immediately around nearby black holes, potentially spotting the shadows of planets against the fiery backdrop of the accretion disk. The search is a testament to human curiosity. We are developing the tools to look for something that, by all rights, should be invisible, using the fundamental laws of physics as our guide. It's a painstaking process of looking for the slightest deviation in the expected, the tiny anomaly in the data that whispers of something extraordinary. Finding a frozen time planet would be one of the most profound discoveries in all of science, not just confirming a wild prediction of relativity, but opening an entirely new window into how planets can form and exist in the most hostile corners of the universe. While the search continues, astronomers have identified a few compelling candidates in our own cosmic backyard where the fabric of time could be stretched to its absolute limit. The most promising location by far is the chaotic, crowded heart of our own Milky Way galaxy, dominated by the supermassive black hole known as Sagittarius A star. This gravitational monster, with a mass over 4 million times that of our Sun, creates a space-time well so deep that it influences the orbits of stars light years away. In recent years, astronomers have tracked a population of strange objects orbiting perilously close to this behemoth. Not just stars, but dusty entities that behave like stars but look like gas clouds. Among this menagerie, there could be planets. The possibility arises from the fact that stars can form in this extreme environment. We've observed young, massive stars in tight orbits around Sagittarius A star, a fact that baffles astronomers because the tidal forces should tear apart the gas clouds needed for star formation. One theory suggests that stars form further out and migrate inward, dragged by interactions with other material. If stars can make this journey, it's conceivable that planets could too, either forming alongside their parent star or being captured later. A planet in a stable orbit just outside the black hole's innermost stable circular orbit would experience time dilation so severe that a single hour on its surface could equate to decades here on Earth. While we haven't confirmed one yet, the dynamic environment makes it a prime hunting ground for such a discovery. Beyond our galactic center, another class of extreme object offers a different pathway to frozen time: binary systems containing neutron stars. A neutron star is the incredibly dense, collapsed core of a massive star that went supernova. Though only the size of a city, a neutron star packs more mass than our Sun, making it second only to black holes in its gravitational might. The surface gravity is so intense that it warps time significantly. Now, imagine a planet that somehow survived the violent supernova that created the neutron star, or one that was captured afterward, orbiting just a few million miles from this ultra-dense remnant. On such a world, time would pass noticeably slower than in the wider universe. While the effect wouldn't be as extreme as near a black hole, where a second might equal a million years, it could still be profound. A day on this planet might equal a year on Earth, or even a century, depending on its orbital distance. The environment, however, would be brutally inhospitable. The planet would be bathed in intense X-rays and gamma rays pouring from the magnetic poles of the rapidly spinning neutron star, a deadly pulsar wind that would sterilize any known form of life and likely strip away any atmosphere. It would be a barren, irradiated rock, but its existence is far more plausible than one around a black hole, as we already know of planets orbiting pulsars. These pulsar planets were among the first exoplanets ever discovered, proving that worlds can indeed form and persist in the most violent aftermaths. These real-world candidates, from the shadow of Sagittarius, a star, to the lethal orbits of neutron stars, transform the concept of frozen time planets from pure theory into a tangible observational challenge. They represent the outermost boundaries of where we believe planetary science and relativity intersect, places where the universe itself becomes a laboratory for testing the most extreme consequences of Einstein's grand vision. Standing on the surface of such a planet would be an experience of profound and eerie stillness, a reality where the very concept of motion has been redefined. The first thing you would notice is the sky, not a dynamic canvas of drifting clouds and moving celestial bodies, but a static, frozen tableau. The stars above would not twinkle, they would be utterly fixed, piercing points of light locked into their positions as if glued to the dome of the heavens. There would be no recognizable constellations, for the slow, proper motion of stars across the galaxy would be completely imperceptible. The entire history of human astronomy, from the first star charts to the present day, would represent less than a single second of observation from this vantage point. You would be looking at a snapshot of the cosmos, a single frame from the universe's grand film, held in place for what feels like an eternity. Any atmosphere this world possesses would contribute to the surreal, dreamlike quality of the environment. If clouds exist, they would not drift or change shape. They would hang in the sky like vast, permanent sculptures, their wispy contours frozen midstream. A storm, if one were occurring, would be a terrifying yet motionless spectacle. Lightning bolts would appear as brilliant, branching structures etched permanently across the sky, not a fleeting flash but a constant, blinding scar of light. Raindrops caught in their descent would hang in the air like a billion glittering diamonds, a mist of suspended animation that you could potentially walk through without ever getting wet. The very air would feel thick and heavy, not with moisture but with the weight of timelessness itself. There would be no wind, no whisper of breeze against your skin, only a silence so deep and complete it feels like a physical presence. The landscape itself would defy everything we know about geology. On Earth, mountains rise and fall over millions of years through the slow dance of tectonic plates. Here, that entire process is compressed into what you would perceive as a few hours, but from your perspective on the ground, the terrain would appear hyper-stable and unchanging. A rock slide triggered by the immense tidal forces would be captured in mid-cascade, a frozen waterfall of boulders and dust hanging precariously on a cliff face. If the planet has any form of volcanic activity, the eruptions would be spectacularly arrested. Fountains of lava would be suspended in great, glowing arcs, and pyroclastic flows would be motionless waves of superheated ash, preserved in their destructive path like insects in amber. The ground under your feet would not shift or settle. It would be as solid and unmoving as the foundations of the universe itself. This creates a paradox of perception that is almost impossible to reconcile. For you, the visitor, your local time flows normally. Your heart beats, your lungs draw breath, and your thoughts form at their usual pace. But the external environment is locked in a state of extreme slow motion relative to you. A falling pebble you kick would take years to land. A wave on a theoretical ocean would take centuries to crest and break. This disconnect between your internal clock and the external world would be the most profound and likely disorienting aspect of the entire experience. You are a being of frantic, fleeting motion trapped in a realm of infinite patience, a single note of sound sustained across a symphony of silence. It is the ultimate expression of relativity, not as an abstract equation, but as a visceral, overwhelming reality that rewrites the very definition of existence. But what if such a world wasn't just a temporary destination for explorers, but a permanent home? This leads us to one of the most speculative and fascinating questions of all. Could life itself arise and evolve in an environment where time is stretched to such an extreme? The biological implications are staggering, suggesting forms of existence so alien that they would challenge our very definition of what it means to be alive. First, consider the fundamental engine of all life, metabolism. For any organism on this planet, its metabolic rate, the speed at which it converts energy to sustain itself, would have to be perfectly synchronized with the local flow of time. A process like cellular respiration that takes a fraction of a second for us might, for them, be a drawn-out chemical reaction lasting decades. Their heartbeats, if they have hearts, could be separated by centuries. A single thought, the firing of a neural network, might unfold over the course of years. This creates a form of existence where patience isn't a virtue, it's a fundamental law of biology. An organism might take 10,000 years to reach out and absorb a single nutrient from the environment, an act of consumption that from our perspective looks like a statue slowly changing its pose over the entire span of recorded human history. Their perception of reality would be equally foreign. To experience the world on this timescale, their senses would be attuned to changes that are imperceptibly slow to us. They might perceive the gradual shifting of tectonic plates as a gentle, rumbling earthquake. The orbit of their planet around the black hole, which might take mere hours from our external view, could feel like a languid, rhythmic cycle lasting eons to them, a seasons changing from light to dark over millions of their years. A more frightening possibility is that their entire reality might be built around sensing phenomena we cannot even detect. They might communicate through gravitational waves, feeling the ripples in space-time from cosmic events as clear signals. Or they might use the slow, predictable decay of radioactive elements within their own bodies as a form of internal clock, a biological Geiger counter ticking once every millennium. Perhaps the most profound difference would be in the pace of evolution. On Earth, evolution is a game of rapid iteration driven by short generations and quick mutations. On a frozen time world, the mechanism would be almost glacial. A single mutation providing a slight advantage might take 1,000,000 years to express itself and become widespread in a population. Natural selection would operate on a canvas of time so vast that it could favor strategies of incredible stability over brute adaptability. Life here wouldn't need to adapt quickly to a changing environment. The environment is essentially permanent and unchanging from their perspective. Evolution would instead select for perfection and resilience. An organism that finds a perfect, sustainable niche could remain unchanged for what we would consider billions of years, becoming a living fossil on a scale we can't comprehend. Their entire evolutionary history, from the first replicating molecule to intelligent life, might span the lifetime of entire galaxies, a slow, deliberate march toward complexity that makes the history of life on Earth look like a fleeting burst of fireworks. This raises a haunting and beautiful possibility. If intelligent life did evolve in such a place, their entire civilization would exist in a state of profound, deliberate slowness. A single conversation between two beings could span the rise and fall of empires on 1,000 worlds elsewhere. A great work of art or literature might be composed over the course of 100 million years, each word or brushstroke considered with a depth of patience we cannot fathom. Their science would be built on observations made over cosmic epochs, allowing them to witness the life cycles of stars firsthand and understand the universe not through snapshots, but through a continuous, eons-long film. They would be the ultimate historians of the cosmos, but their very nature would make contact with any other form of life almost impossible. By the time they finished receiving a single transmission from another civilization, that civilization would have likely been extinct for ages, their message nothing more than a ghost from a forgotten past echoing into eternity. Yet the most daunting barrier to exploring such a world isn't the technology or the radiation. It's the psychological and emotional chasm created by the time dilation itself. The moment an exploration vessel enters that extreme gravitational field, a terrible and irreversible schism would open up between the crew and everyone they have ever known. For the astronauts, the mission might last a few years, time enough to conduct their surveys, take their samples, and begin the journey home. But for everyone on Earth, and indeed for the entire universe outside that gravitational well, millions of years would have passed. The civilization they left behind would be unrecognizable if it even still existed. Humanity could have evolved into a new species, ascended to a post-biological state, or vanished entirely into the dust of history. They would be returning as the ultimate relics, archaeological artifacts of a forgotten age coming home to a world that has no memory of them. This creates a paradox of purpose that is almost impossible to overcome. What would be the point of gathering scientific data to bring back to Earth if the people who commissioned the mission have been dead for 1,000,000 millennia? The very concept of returning loses all meaning. The crew would have to confront a loneliness so profound it transcends human experience. They are not just leaving their families, they are leaving their entire epoch, severing themselves from the flow of history itself. Every minute they spend on the surface, they are consciously watching the future of their species flash before their eyes at an incomprehensible speed, powerless to interact with it. The psychological preparation for such a mission would require a fundamental rewiring of human attachment and purpose, fostering a detachment from all of humanity's past and future that is almost monastic in its totality. The physical challenges, while more tangible, are equally forbidding. Even with a ship capable of shielding them from the intense radiation and withstanding the gravitational tides, the act of entering and leaving such a deep gravitational well would demand staggering amounts of energy. To descend into the well and then climb back out requires overcoming the black hole's phenomenal pull, a feat that likely necessitates engines and power sources far beyond anything we can currently conceive. Furthermore, the act of communication would be rendered useless. A simple question radioed back to mission control would take thousands of years to arrive, and the answer would return tens of thousands of years later, long after the crew had perished. The mission would be one of utter isolation, a one-way journey into the unknown with no possibility of guidance or support from home. Ultimately, a mission to a frozen time planet would be less of an exploration and more of a permanent exile. The astronauts would become time castaways, choosing to sacrifice their place in the human timeline for the sake of pure knowledge. They would witness the death of stars and the reshaping of galaxies from their unique vantage point, becoming silent, eternal observers of the cosmos. Their greatest legacy would not be the data they brought back, but the simple, monumental act of having been there, a testament that a species born to the brief flash of a spark dared to reach out and touch the face of eternity. This fundamental disconnect in the flow of time creates a communication barrier so absolute it makes the vast distances of space seem trivial by comparison. Even if we could build a transmitter powerful enough to send a signal into the extreme gravitational well surrounding such a planet, the act of conversation would be rendered meaningless by relativity itself. Imagine an astronaut on the surface wanting to send a simple status report back to mission control on Earth. They compose the message, "All is well," beginning initial surveys, and press the transmit button. From their perspective, the radio waves travel outward at the speed of light. But as those signals fight their way out of the profound gravity of the black hole, they are sapped of energy, their wavelengths stretched and redshifted. More importantly, each second of that transmission's journey to freedom represents an ever-increasing amount of time passing in the outside universe. By the time that faint, stretched signal finally escapes the gravitational grip and reaches a receiver near Earth, thousands of years may have passed. The scientists who launched the mission, their entire civilization, and the very language they spoke would be ancient history. The message would be nothing more than an archaeological curiosity, a whisper from a long-dead explorer. Now consider the response. Earth, upon finally receiving this millennia-old signal, might send a reply, "Message received. What are your findings?" That return transmission would then have to plunge back into the gravitational well, again undergoing the same incredible time dilation. By the time that answering signal finally reached the astronaut on the planet's surface, millions of years could have passed from their external perspective. The astronaut would have only just finished speaking their original message, their mouth closing as the reply from a forgotten future finally arrives. A single, two-part exchange of greetings would have spanned the lifetime of a species. This transforms any attempt at dialogue into a series of lonely, cosmic monologues flung into the void, with no expectation of a timely or even relevant answer. The very concepts of real-time or live communication cease to have any meaning. For the inhabitants of such a world, if any could exist, the universe outside would appear to be a blindingly fast, incomprehensible blur. Any signals they might detect from other civilizations would be compressed into an unintelligible, high-frequency screech, like a recording played at thousands of times its normal speed. Conversely, any signal they send out would be so dramatically slowed down that to an external listener, it would sound like a single, deep, drawn-out note lasting for centuries, containing no discernible information. There is no common time frame, no shared rhythm upon which to build a connection. They are forever locked in their own slow-moving bubble of reality, able to observe the universe but never truly interact with it in any way that we would recognize as communication. This mind-bending concept hasn't been lost on storytellers. In fact, science fiction has long used time dilation as a powerful narrative device to explore profound themes of love, loss, and the human condition when faced with the cosmos's immense scales. Perhaps the most scientifically grounded and emotionally resonant portrayal is found in Christopher Nolan's film Interstellar. The depiction of Miller's planet, a water world orbiting just outside the event horizon of the supermassive black hole Gargantua, is a masterclass in translating theory into visceral drama. The crew's desperate race against the rising tides, where every hour on the surface costs them 23 years back on Earth, perfectly captures the terrifyingly asymmetric flow of time. The film's scientific consultant, physicist Kip Thorne, ensured the portrayal of gravitational time dilation was as accurate as possible, making the emotional stakes feel not just fantastical but tragically inevitable. The heart-wrenching result, astronaut Cooper watching decades of video messages from his children, seeing their entire lives unfold in a matter of minutes, is a powerful analogy for the real, albeit less extreme, time slippage that occurs with every astronaut we send into orbit, just amplified to a soul-crushing degree. Television has also frequently played with these ideas, often using them as a convenient plot mechanism to explore alternate futures or pasts. The Star Trek franchise, for instance, has returned to the well of time dilation multiple times. In the classic original series episode, Wink of an Eye, the crew of the Enterprise encounters a society whose accelerated metabolism makes them invisible and inaudible to normal human perception, a clever inversion of the typical frozen time planet scenario. Here, it's not the environment that's altered, but the people themselves, creating a similar disconnect in the flow of experience. Another notable example is from Star Trek: The Next Generation in the episode Cause and Effect, where the Enterprise is caught in a temporal causality loop, experiencing the same events repeatedly while only seconds pass for the outside universe. While not strictly gravitational time dilation, these stories use the concept of relative time to create tension and mystery, simplifying the complex physics into a more digestible, character-driven dilemma. Other works take a more metaphorical approach. Joe Haldeman's seminal novel The Forever War uses velocity-based time dilation as a central metaphor for the alienation of soldiers returning from conflict. As the protagonist engages in interstellar battles at near light speed, each mission lasts months for him but sees centuries pass on Earth. He returns again and again to a home that becomes increasingly foreign, his comrades aging and dying while he remains young, a poignant commentary on how war separates individuals from the society they fight for. This contrasts sharply with the more common gravitational portrayal, but is equally valid under Einstein's theories, showing how science fiction can mine different aspects of relativity for narrative depth. However, these fictional accounts almost universally take creative liberties for the sake of story, compressing or simplifying the truly alien reality. Most stories ignore the absolutely lethal ancillary conditions: the crushing gravity, the intense radiation, the spaghettifying tidal forces that would accompany the time dilation effect near a black hole. A person standing on Miller's planet would be flattened into a puddle by the immense gravity long before they had to worry about the tides, and the energy required to enter and leave such a deep gravitational well is hand-waved away with future technology. Furthermore, the psychological impact is often condensed into a single, dramatic scene of revelation, when in reality the disorientation and isolation would be a constant, overwhelming state of being, a profound existential crisis unfolding in slow motion from the perspective of the crew. Despite these necessary simplifications, the value of these portrayals is immense. They act as a gateway, introducing millions of people to a complex scientific principle through the power of emotion and narrative. They make the abstract tangible. We may not remember the exact equation for gravitational time dilation, but we remember the look on Cooper's face as he watches his daughter grow old without him. That emotional hook creates curiosity, driving a deeper interest in the actual science behind the story. These fictional explorations serve as a crucial bridge between the cold, hard math of general relativity and the human experience, allowing us to not just understand time dilation intellectually, but to feel its staggering implications in the very core of our being. But to truly push our understanding of these frozen realms to its absolute limit, we must venture beyond the cosmic scale of relativity and into the subatomic world of quantum mechanics. This is where the laws governing the very small meet the mind-bending effects of the very massive, creating a paradox that challenges the foundations of physics itself. In our everyday world, time dilation is a smooth, predictable effect described by Einstein's equations. But in the quantum realm, time is not a smooth river, it's a series of discrete, probabilistic events. So what happens to the bizarre rules of quantum physics when time is stretched to an absolute crawl? Consider a fundamental quantum process like radioactive decay. Here on Earth, we can predict with remarkable accuracy that half of a large sample of uranium atoms will decay in about 4.5 billion years. But we can never predict which specific atom will decay and when. It is a completely random, probabilistic event. This inherent unpredictability is a cornerstone of quantum theory. Now picture that same sample of uranium on the surface of our frozen time planet. From our external perspective, watching from a safe distance, the entire process of radioactive decay would appear to slow to an unimaginable crawl. What was a half-life of billions of years would now seem to take trillions upon trillions of years, but crucially, the quantum randomness would remain. We still wouldn't be able to predict which atom decayed when. The process is just stretched out like a film playing at an infinitesimally slow speed. This leads to a truly bizarre possibility. For an observer on the planet's surface, their local time is normal. They could, in theory, set up a detector to observe these uranium atoms. In their frame of reference, the atoms would be decaying at their usual, random intervals. They might see one atom decay, then wait a few minutes or hours for the next one. But from our external view, those two decay events might be separated by thousands of years. This creates a profound disconnect in how events are ordered in time. An event that seems consecutive and closely spaced for the local observer is separated by an immense gulf of time for the external universe. It forces us to ask which perspective is the real one. Quantum mechanics suggests there may not be a single answer, that reality itself is observer-dependent. The implications become even stranger when we consider quantum superposition, the famous idea that a particle can exist in multiple states at once until it is observed. Think of Schrödinger's cat, the thought experiment where a cat in a box is simultaneously alive and dead until someone looks inside. Now place that box on our frozen time planet. For an astronaut standing right next to the box, the quantum superposition would presumably resolve in a normal amount of their local time. They open the box and find either a live or a dead cat. But for us, watching from afar, that single act of observation could be stretched out over millennia. Would we see the cat remain in its blurred, superpositional state for thousands of years before suddenly collapsing into a definite state? Or would the act of observation itself, happening at a specific point in the astronaut's time, send a signal to the universe that instantly resolves the superposition across all reference frames? This touches on one of the biggest unsolved problems in physics, the measurement problem, which asks why the act of observation causes a probability wave to collapse into a definite reality. Extreme time dilation could provide a unique, if entirely theoretical, laboratory to study this. If the collapse appears to happen at different rates for different observers, it might offer clues about whether consciousness, or simply interaction with a larger system, is the true trigger. It suggests that the transition from the fuzzy quantum world to the definite classical world we experience might not be a universal instant, but a process that itself is subject to the relativistic warping of time. Perhaps the most significant contribution of the quantum perspective is the introduction of a limit. In the perfect, smooth spacetime of general relativity, time dilation can increase without bound as you approach the event horizon. But quantum physics introduces graininess into the universe through the Planck scale, the smallest possible units of time and space. Many physicists theorize that you cannot have a meaningful measurement of time shorter than the Planck time, an interval so brief it is to a second what a second is to hundreds of trillions of years. This presents a potential boundary, as time dilation stretches a local second to cover millions of external years. The external universe's ability to resolve what's happening on the planet might hit a fundamental limit. Beyond a certain point of dilation from our view, the planet's timeline would become a continuous blur, its events happening at a rate slower than the Planck time. This could mean that the intricate quantum processes on that world simply cannot be described or measured by any external observer. they become lost in the fundamental graininess of space-time. The planet would effectively fade from the observable universe, not because it vanishes, but because its clock ticks so slowly that it ceases to interact meaningfully with the rest of reality. It becomes a ghost world, its existence confirmed only by its gravitational shadow, its internal richness forever hidden behind a veil of timelessness, a secret the universe keeps even from itself. This unique property transforms these frozen worlds into the universe's ultimate observatories, offering a front-row seat to cosmic events that normally unfold in a blinding flash. From our earthly perspective, many of the most energetic and fascinating processes in the cosmos are over in an instant. A supernova, for instance, reaches its peak brightness in a matter of days before fading away over months. The collision of two neutron stars unleashes a torrent of gravitational waves and light in a violent outburst that is measured in seconds. Even the volatile weather on a distant brown dwarf or the flare from a young red dwarf star can come and go too quickly for our telescopes to capture every intricate detail. But from the surface of a planet where time is stretched to an extreme, these frantic cosmic fireworks would appear to unfold in exquisite, deliberate slow motion. Imagine setting up an observatory on such a world, pointed towards a region of space where a supernova is about to occur. For astronomers on Earth, the event is a frantic race against time, a brief celestial explosion that demands round-the-clock observation to catch every precious piece of data. From our frozen vantage point, that same supernova would blossom across the sky with the graceful, unhurried pace of a flower opening at dawn. The initial shockwave breaking through the star's surface might take what feels like weeks to develop, allowing researchers to study its complex structure in unprecedented detail. The subsequent rise to peak brightness could unfold over the course of years, providing an open-ended opportunity to analyze the chemistry of the expanding cloud, test models of stellar death, and observe the creation and dispersal of heavy elements that will one day form new planets and life. An event that is a fleeting spectacle everywhere else becomes a multi-generational study project, a celestial laboratory experiment unfolding in slow motion. This slow-motion view wouldn't just apply to cataclysms, it could revolutionize our understanding of dynamic but slower processes. The intricate dance of a binary star system, normally taking centuries to complete a single orbit, might be condensed into a manageable observational period. We could watch the gravitational interactions, mass transfer, and tidal distortions play out over a few local years. The formation of a solar system, a process that takes tens of millions of years, might be observable from start to finish within a single lifetime on this world, allowing us to witness the birth of planets from the primordial disk in real time. Even the large-scale structure of the universe itself could be studied anew. The drift of galaxies, the subtle proper motion of stars within them, and the slow evolution of galaxy clusters would no longer be inferred from comparing ancient photographs. They would be directly visible as a continuous, flowing motion in the sky, a grand celestial clock with hands we could watch move. The scientific value of such a perspective is almost beyond calculation. It would allow for the testing of astrophysical models with a precision we can only dream of today. Theories about stellar evolution, gravitational wave emission, and accretion disk physics could be compared against perfectly detailed, slow-motion recordings of the actual events. It would be like having a universal remote control for reality, with a permanent pause and slow-motion button applied to the entire cosmos. Any transient event, no matter how brief its standard duration, becomes a permanent, open book for study. This turns the concept of astronomy on its head. Instead of being passive observers of a universe that operates on timescales far beyond our own, we could step into a reference frame where the universe's most dramatic processes align with human patience, granting us a God's-eye view of creation itself. The laws of thermodynamics govern everything from the steam in your kettle to the nuclear fires of a star, But how would they operate on a world where time itself has been stretched to an almost standstill? The implications are as profound as they are bizarre, forcing us to reconsider the very nature of energy, disorder, and change. To begin with, let's consider the simplest of these laws, the conservation of energy. This principle states that energy cannot be created or destroyed, only transformed from one form to another. On a normal planet, this is a dynamic, constant process. Chemical energy in wood becomes heat and light in a fire, which then radiates out into space. On our frozen time world, this fundamental process would be rendered almost unrecognizable. A single log burning in a fireplace would, from our external perspective, appear to be a source of perpetual frozen flame. The chemical reactions within the wood, which usually take seconds, would be drawn out over millennia. The flames would appear motionless, a beautiful but terrifying sculpture of light and heat that barely flickers over the course of centuries. The energy is still being conserved and converted, but the rate of that conversion has been slowed to an absolute crawl, making the process seem static and eternal. This leads us directly to the second law of thermodynamics and its famous, relentless driving force, entropy. Entropy is a measure of disorder, and the second law states that the total entropy of an isolated system can never decrease over time. In our everyday experience, this is the reason ice melts in a drink, why buildings eventually crumble, and why we ourselves age. It's the universe's inevitable slide from order to disorder. But what happens to entropy when over time means something entirely different? From the viewpoint of an external observer, the entropy on this frozen planet would appear to be almost frozen itself. The inevitable decay and breakdown of all structures and systems would be imperceptibly slow. A castle made of sand on the beach wouldn't be eroded by wind or waves for what we would measure as millions of years. The planet's entire system would seem to be locked in a state of suspended animation, defying the usual, visible march of time and decay that we see everywhere else in the universe. However, for an observer actually living on the planet's surface, the experience would be completely inverted. In their local time frame where time flows normally, the second law of thermodynamics would operate exactly as it always does. That sandcastle would still weather and fall apart, but it might take 10,000 of their years to do so. Their sun, if they had one, would still be converting mass to energy and radiating it away, increasing the entropy of the universe. The key difference is one of perspective. The universe outside is racing forward at a blinding pace, its entropy increasing in a frantic rush, while the entropy increase within the planet's gravitational well is a slow, deliberate, and almost dignified procession. This creates a stunning paradox. The planet would appear to be a bastion of order and low entropy from the outside, while from the inside, it is subject to the same relentless thermodynamic decay as any other place, just at a pace that is perfectly synchronized with its own glacial timeline. The most dramatic thermodynamic consequence involves heat itself. Heat transfer is the process of thermal energy moving from a warmer area to a cooler one, and its rate is fundamentally tied to the flow of time. On Earth, a hot cup of coffee left on a table will cool to room temperature in maybe an hour as heat energy dissipates into the surrounding air. Now, place that same cup of coffee on the surface of our frozen time planet. From our distant vantage point, the cooling process would be astonishingly slow. The heat would seem reluctant to leave the cup, its journey into the cooler environment drawn out over epochs. The coffee would appear to stay hot for centuries, but for someone standing right next to the cup, the experience would be perfectly normal. They would feel the heat on their hand, and if they waited, they would feel it gradually cool down over what to them was a standard amount of time. This disconnect highlights how thermodynamics, like everything else, is relative. The rate of physical processes is not absolute, it is intimately woven into the local fabric of space-time. This has a staggering implication for the planet's own energy balance and climate. Any internal heat source, whether from a molten core warmed by tidal forces or from residual radioactive decay, would release its energy at this incredibly slowed rate. The planet's surface temperature would be incredibly stable over what we consider astronomical timescales, not because it lacks energy, but because the release and dissipation of that energy is happening on a timeline that is almost impossible for us to measure from the outside. The planet would be a thermodynamic island operating on its own watch, obeying all the universal physical laws but doing so at a pace that makes it seem, from our frantic perspective, like a perfectly preserved fossil of a moment in time, forever caught between order and chaos. But the orbital dance near such a monstrous object is far more complex and beautiful than a simple, static circle. To understand the true motion of a planet skirting a black hole, we must move beyond the familiar clockwork of Newtonian gravity and into the warped geometry of Einstein's general relativity. In our solar system, Newton's laws do a superb job of predicting the orbits of planets. They are, for the most part, stable ellipses that repeat with clock-like regularity. A planet like Mercury exhibits a tiny, almost imperceptible drift in its orbit over time, a phenomenon called precession. But even this is largely explainable by the gravitational tug of other planets. Near a black hole, however, the rules of the game change entirely. The sheer curvature of space-time itself becomes the dominant force, introducing dramatic effects that would make Newton's head spin. The most striking of these relativistic effects is the drastic increase in orbital precession. In simple terms, precession means the planet's elliptical path doesn't quite close upon itself. Instead of retracing the same ellipse with each orbit, the point of closest approach, the perihelion, or in this case, the parabothron, slowly rotates around the black hole. From above, the planet's path would look like a beautiful, intricate spirograph pattern, a rosette slowly painting itself around the abyss. While Mercury's orbit precesses by a tiny fraction of a degree per century, a planet near a black hole could see its entire orbit precess by many degrees in a single pass. This isn't caused by the pull of other planets. It is a direct result of the black hole's mass warping the very stage upon which the planet moves. The planet is simply following the shortest path through curved space, and that path itself is constantly evolving. This has profound implications for the long-term stability of such a world. In a Newtonian system, a stable orbit is just that stable. Barring some external influence, a planet could theoretically orbit a star forever. In the relativistic environment around a black hole, stability is a far more precarious and fleeting concept. The extreme precession can actually make certain orbits chaotic over long periods. A planet might have a stable-looking orbit for thousands of revolutions, but the cumulative effect of the precession could eventually resonate with other gravitational influences, perhaps from the accretion disk or other nearby objects, eventually kicking the planet into a wildly different path, either sending it careening into the void or dooming it to a final, fatal plunge across the horizon. Finding a truly stable, long-term orbit in this environment is like finding a single, specific needle in a haystack the size of a galaxy. Furthermore, the concept of a simple, closed elliptical orbit completely breaks down. General relativity predicts the existence of those innermost stable circular orbits we discussed, the ISCO. Within this boundary, no stable circular orbit can exist at all. Any object that ventures inside is fated to spiral inward, its fate sealed. A planet surviving here must exist in a delicate balance precisely outside this point. But even its orbit wouldn't be a perfect circle or ellipse in the classical sense. The path is fundamentally geodesic, meaning it's the straightest possible line through a profoundly curved geometry. From our flat space perspective, this path appears as a precessing ellipse, but it is, in reality, the planet simply moving freely along the contours of spacetime itself, like a marble rolling around a deeply curved funnel. The differences from Newtonian predictions are not minor tweaks, they are fundamental and dramatic. A Newtonian physicist calculating the orbit of such a planet would get it catastrophically wrong. They would predict a stable, repeating ellipse and would be completely baffled by the massive precession and the potential for chaotic instability. They would miss the core truth that the force of gravity isn't a mysterious pull across distance, but the natural motion of an object following the curved geometry of the universe. This environment is a pure and violent demonstration of Einstein's genius, a place where his theory isn't a small correction but the only set of rules that applies. The orbit of a frozen time planet is not a path through space, it is a ripple in space-time, a permanent record of the profound and beautiful warping of reality itself. Yet it is the profound puzzle of consciousness that presents the most deeply personal and unsettling implication. Our sense of self, our stream of thought, is intrinsically tied to the flow of time. Consciousness is a process, a narrative we construct from one moment to the next. But what becomes of that narrative when the external world provides no feedback, no change for what feels like an eternity? A being living its entire life on such a world would experience a reality of incredible stability and sameness. Their thoughts, unfolding at a normal local pace, would be met with an environment that is essentially static. A single, continuous observation of a fixed starscape could form the backdrop for an entire lifetime of internal contemplation. This could foster a form of consciousness far more introspective, patient, and perhaps even tranquil than our own, a mind utterly detached from the frantic rush of cosmic events, its identity forged not through interaction with a changing world, but through the slow, deep currents of its own internal universe. Conversely, consider the consciousness of a visitor from our normal time frame. They would be trapped in a terrifying disconnect. Their mind would race at its usual pace, demanding stimulation, change, and progress, while the external world would refuse to oblige. The psychological toll would be immense, a recipe for madness born from a starvation of novelty. This starkly highlights that our very minds are products of our temporal environment. We are thinking machines built for a universe of moderate change and a steady, familiar rhythm. Placing us in a realm where that rhythm is distorted beyond recognition forces us to ask whether consciousness itself is a universal constant or a local adaptation, shaped and defined by the specific flow of time in which it evolved. These frozen worlds ultimately force us to confront the most fundamental question of all: what is real? Is reality the local, subjective experience of the individual, where time feels normal and the universe is a blur? Or is it the objective, external view from afar, where that same individual is a frozen statue in a forgotten corner of space? Physics provides the equations to describe both perspectives, but philosophy is left grappling with the meaning. There is no universal now, no privileged clock ticking at the center of the universe. There are only reference frames, each with its own equally valid claim on reality. A frozen time planet is the ultimate expression of this relativistic truth, a place where the concept of a single, shared reality dissolves into a multitude of personal, temporal experiences, each isolated and incommunicable, yet all equally true within their own domain. This unique property transforms these frozen worlds into the universe's ultimate observatories, offering a front-row seat to cosmic events that normally unfold in a blinding flash. From our earthly perspective, many of the most energetic and fascinating processes in the cosmos are over in an instant. A supernova, for instance, reaches its peak brightness in a matter of days before fading away over months. The collision of two neutron stars unleashes a torrent of gravitational waves and light in a violent outburst that is measured in seconds. Even the volatile weather on a distant brown dwarf or the flare from a young red dwarf star can come and go too quickly for our telescopes to capture every intricate detail. But from the surface of a planet where time is stretched to an extreme, these frantic cosmic fireworks would appear to unfold in exquisite, deliberate slow motion. Imagine setting up an observatory on such a world, pointed towards a region of space where a supernova is about to occur. For astronomers on Earth, the event is a frantic race against time, a brief celestial explosion that demands round-the-clock observation to catch every precious piece of data. From our frozen vantage point, that same supernova would blossom across the sky with the graceful, unhurried pace of a flower opening at dawn. The initial shockwave breaking through the star's surface might take what feels like weeks to develop, allowing researchers to study its complex structure in unprecedented detail. The subsequent rise to peak brightness could unfold over the course of years, providing an open-ended opportunity to analyze the chemistry of the expanding cloud, test models of stellar death, and observe the creation and dispersal of heavy elements that will one day form new planets and life. An event that is a fleeting spectacle everywhere else becomes a multi-generational study project, a celestial laboratory experiment unfolding in slow motion. This slow-motion view wouldn't just apply to cataclysms, it could revolutionize our understanding of dynamic but slower processes. The intricate dance of a binary star system, normally taking centuries to complete a single orbit, might be condensed into a manageable observational period. We could watch the gravitational interactions, mass transfer, and tidal distortions play out over a few local years. The formation of a solar system, a process that takes tens of millions of years, might be observable from start to finish within a single lifetime on this world, allowing us to witness the birth of planets from the primordial disk in real time. Even the large-scale structure of the universe itself could be studied anew. The drift of galaxies, the subtle proper motion of stars within them, and the slow evolution of galaxy clusters would no longer be inferred from comparing ancient photographs. They would be directly visible as a continuous, flowing motion in the sky, a grand celestial clock with hands we could watch move. The scientific value of such a perspective is almost beyond calculation. It would allow for the testing of astrophysical models with a precision we can only dream of today. Theories about stellar evolution, gravitational wave emission, and accretion disk physics could be compared against perfectly detailed, slow-motion recordings of the actual events. It would be like having a universal remote control for reality, with a permanent pause and slow-motion button applied to the entire cosmos. Any transient event, no matter how brief its standard duration, becomes a permanent, open book for study. This turns the concept of astronomy on its head. Instead of being passive observers of a universe that operates on timescales far beyond our own, we could step into a reference frame where the universe's most dramatic processes align with human patience, granting us a God's-eye view of creation itself. The mind-bending physics of frozen time planets does more than just describe a distant cosmic curiosity. It opens a door to a future where humanity might not just find such places but learn to build them. The ability to control the flow of time itself has been a staple of science fiction for generations, but the scientific principles we've explored suggest it could be more than just fantasy. By studying how gravity warps spacetime around black holes, we begin to sketch the blueprints for theoretical technologies that could one day allow us to create localized fields of altered time, turning a universal constant into a variable we can engineer. The most promising path toward this staggering capability lies in the manipulation of gravity. We've seen that immense gravitational fields are the key to severe time dilation. So, if we could artificially generate or concentrate a gravitational field without the need for a black hole's destructive power, we could theoretically create a time chamber here on Earth. One concept involves the theoretical existence of negative mass. In Einstein's equations, a large concentration of negative mass would produce a gravitational repulsion, but it could also warp spacetime in ways that are even more exotic than a black hole. If we could somehow contain a stable volume of this hypothetical substance, we might be able to construct a region where time flows at a radically different rate compared to its surroundings. An object placed inside this field might experience hours while only seconds pass outside, or vice versa, depending on the configuration. Another avenue explores the potential of ultra-dense exotic materials. While we lack anything near the density of a black hole, advancements in material science and our understanding of quantum gravity could one day lead to metamaterials or condensed matter states that can mimic these extreme space-time curvatures on a small, controlled scale. Imagine a device that uses intense, precisely focused energy fields to momentarily twist the local fabric of space-time, creating a temporary bubble where time is slowed or sped up. This wouldn't require moving entire planets. It could be a localized effect contained within a laboratory or perhaps even a spacecraft. The energy requirements for such a feat are currently beyond imagination, but the physics does not explicitly forbid it. The applications of such a technology would redefine human civilization. In medicine, a time dilation field could be used to slow biological processes, placing critically injured patients into a state of suspended animation, giving surgeons what would feel like days to perform intricate operations while only minutes pass in the outside world. For long-distance space travel, a ship enveloped in a field where time flows slower internally would allow a crew to travel for what feels like a few years to them, while centuries pass in the wider universe, effectively allowing them to leapfrog across galactic distances without succumbing to age. Conversely, for scientific research, a field that speeds up time locally could allow us to observe processes that are normally too slow, like the formation of crystals or the growth of plants, in a highly accelerated time frame. Of course, the challenges are as monumental as the potential. Creating and stabilizing such a violent distortion of spacetime would demand energies on a scale we can scarcely conceive, likely requiring power sources far beyond our current capabilities, such as harnessing the energy of entire stars. Containing the field would be another immense hurdle. A malfunction could have catastrophic consequences, unleashing uncontrolled gravitational tides or creating unpredictable temporal paradoxes. There are also profound philosophical and ethical questions. Who would control such an power? How would it affect our concept of a shared human experience if different groups could exist in entirely different timelines? The societal disruption would be unprecedented, yet the pursuit of this understanding is invaluable, even if the technology remains forever out of reach. By stretching our minds to grapple with these ultimate possibilities, we push the boundaries of physics, engineering, and philosophy. We are forced to ask deeper questions about the nature of reality itself. The dream of controlling time pushes us to become a more curious, more ambitious species, always reaching for a deeper understanding of the universe and our place within it. The frozen time planets out in the cosmos are not just wonders to be observed. They are the universe's most extreme teachers, showing us the raw potential of physical law and inviting us to imagine what we might one day achieve. But the allure of witnessing time itself stretch to its limits comes with a terrifying price tag of physical peril, a suite of dangers so extreme they defy easy comprehension. The first and most visceral threat is the phenomenon of tidal forces. We experience mild tidal forces on Earth, the moon's gravity gently pulling on our oceans to create the tides. But near a black hole, this gentle pull is transformed into a monstrous destructive strain. Gravity's strength increases dramatically with proximity, meaning the force exerted on your feet would be exponentially stronger than the force on your head if you were falling feet first. Even before you reach the event horizon, this difference in pull would stretch your body lengthwise into a long, thin strand, a process physicists grimly call spaghettification. A planet orbiting in this region would be subject to these same forces on a global scale, likely kept in a constant state of tectonic agony, its surface perpetually flexing and cracking from the incredible strain, making it a world of endless earthquakes and volcanic eruptions. Beyond the crushing gravity lies an invisible, equally lethal hazard, an onslaught of radiation. the accretion disk of a supermassive black hole isn't just a pretty ring of light. It's a maelstrom of superheated plasma, charged particles, and magnetic fields of unbelievable power. Matter spiraling inward is accelerated to near light speed, and the friction and magnetic processes heat it to millions of degrees, causing it to emit high-energy X-rays and gamma rays. Any planet or spacecraft venturing near this environment would be bombarded by this lethal radiation, a constant storm that would instantly fry electronics, destroy organic tissue, and strip away any atmosphere. The very act of looking toward the black hole could be blinding, as the intense light pouring from the accretion disk would carry enough energy to cause irreparable damage. Surviving here wouldn't just require a strong hull, it would require shielding of a magnitude we can scarcely imagine, perhaps using forces, fields, or materials woven from the very fabric of spacetime itself. Perhaps the most insidious danger is one that isn't violent or explosive, but absolute and final, the point of no return. This isn't just a dramatic phrase, it's the physical boundary of the event horizon. From the perspective of an outside observer, as an object approaches this boundary, its time dilation increases toward infinity. It appears to slow down, redden, and fade, seemingly frozen forever on the edge. But for the traveler, crossing this horizon might be uneventful. There is no sudden jerk, no dramatic alarm. The true danger is the irreversible severing of your connection to the entire universe. Once across, no force in the universe can push you back out. Every path forward leads inexorably downward toward the singularity at the center. You could fire your engines at full power directly away from the black hole, and it would be as futile as trying to sail a boat upstream of a waterfall that has already been crested. There is no going back, no sending a final message, no warning to those who follow. It is the ultimate one-way trip, a journey into a realm from which not even information can escape to tell the tale. The quest to move from theory to direct observation of these incredible time-warped environments is driving some of the most ambitious projects in modern astronomy. While we can't yet send probes to a black hole, we are building the next generation of eyes to study them from afar with unprecedented clarity. The James Webb Space Telescope has already revolutionized infrared astronomy, peering through cosmic dust to study the hearts of distant galaxies. But its successor, the Nancy Grace Roman Space Telescope, is specifically designed for wide-field surveys that could indirectly reveal these hidden worlds. By monitoring the hearts of millions of galaxies for the subtle, telltale signatures of gravitational microlensing, Roman might just catch the rare event of a black hole's gravity magnifying a distant star, with a tiny, repeated wobble in the signal betraying the presence of an orbiting planet. This is the painstaking, statistical hunt for a needle in a cosmic haystack, requiring patience and immense computational power to sift through the data for that one in a billion anomaly. Even more powerful ground-based observatories are on the horizon. The extremely large telescope currently under construction in the Chilean desert will gather more light than any other optical instrument in history. With a main mirror stretching nearly 40 meters across, its resolution will be sharp enough to directly observe the individual stars orbiting much closer to our own galactic center, Sagittarius A, than ever before. By tracking their precise movements over years, astronomers could detect the faintest gravitational tug of an unseen, massive planet shepherding them, its presence inferred by a slight deviation in a star's expected path. This is like watching a vast cosmic dance and noticing one dancer is being subtly led by an invisible partner. Each new telescope acts as a finer sieve, allowing us to filter out the noise of the universe and isolate the faint signals of these extreme worlds. The ultimate dream, of course, is to send a robotic probe. While a mission to another star system remains a distant goal, a more plausible target for a future, hyper-advanced civilization might be a closer supermassive black hole like the one at the core of our galaxy. Conceptual mission plans already exist for such a daunting undertaking. A potential robotic scout would need to be incredibly autonomous, as any signal sent back to Earth would take over 26,000 years for a one-way trip. It would require propulsion systems we can barely imagine, perhaps harnessing the energy of antimatter or nuclear fusion to accelerate to a significant fraction of light speed. Its hull would need to be engineered from materials that can withstand not only the immense radiation and particle bombardment near the accretion disk, but also the phenomenally powerful tidal forces that threaten to spaghettify any object that ventures too close. The most critical phase of the mission would be the approach and orbital insertion. The probe wouldn't aim for a standard orbit. It would need to achieve a precise balance within the innermost stable circular orbit, that precarious zone where time dilation becomes extreme. Even a minor miscalculation would send it careening across the event horizon, its final data upload forever lost to the universe. Assuming it succeeded, its instruments would begin a program of unprecedented science. Its first task would be to deploy a series of ultra-precise atomic clocks. By comparing the tick rate of these clocks to identical ones back in the solar system, we would have the first direct experimental measurement of severe gravitational time dilation, putting Einstein's predictions to the ultimate test. Other sensors would map the magnetic field structure of the accretion disk, analyze the composition of matter just moments from its final plunge, and perhaps even attempt to image the event horizon's shadow from an unimaginably close vantage point. The data returned would be the most valuable in human history, but the act of retrieving it presents another profound challenge. As the probe enters the extreme gravitational field, the signals it sends back will experience that same drastic time dilation. The initial "we have arrived" transmission might be sent, but from our perspective on Earth, the data stream would slow to a crawl. A single packet of information containing a day's worth of readings for the probe could take centuries to fully transmit to our receivers. We would be forced to adopt a multi-generational approach to this single experiment, with scientists dedicating their entire lives to receiving and interpreting a fragment of a dataset that is, from the probe's point of view, being sent in real time. This mission would be the epitome of long-term scientific commitment, a project where the principal investigators would never live to see the final results, planting a tree whose fruit would be enjoyed by their distant descendants thousands of years in the future. So as we pull back from the edge of this theoretical abyss, we're left with a staggering realization. Frozen time planets are not just science fiction. They exist within the rigorous framework of Einstein's general relativity, a breathtaking testament to a universe far stranger and more wonderful than we often allow ourselves to imagine. These are places where the very constants of our existence are rewritten, where a single moment can hold the weight of ages, and where the flow of time itself becomes a tangible landscape of mountains and valleys. They challenge our most fundamental perceptions, forcing us to accept that there is no universal clock, no single now that governs all of reality. Instead, our experience is a local phenomenon, a personal rhythm dictated by our specific place in the cosmos. This journey through extreme physics does more than just satisfy our curiosity. It fundamentally stretches the limits of our understanding. It asks us to contemplate realities where biology, consciousness, and even the laws of thermodynamics operate on scales we can scarcely fathom. We're invited to consider not just how the universe works, but how it might be experienced from an infinite number of perspectives, each equally valid within its own frame of reference. The existence of such possibilities, whether natural around a black hole or perhaps one day engineered through a profound mastery of physics, expands our sense of what is possible. It transforms the cosmos from a distant, impersonal void into a dynamic tapestry of potential experiences, each more incredible than the last. And this is perhaps the most beautiful takeaway. The universe is still packed with profound mysteries waiting to be uncovered. For every question we answer about frozen time, a dozen more emerge about quantum gravity, the nature of singularities, or the possibility of other, even more exotic forms of matter and energy. The deepest reaches of space-time are not empty. They are teeming with potential, with secrets that defy our current comprehension and invite a future of endless discovery. This isn't the end of a conversation, it's an invitation to a much larger one. Now we want to hear from you. Which part of this incredible concept captured your imagination the most? Was it the sheer physics of time dilation around a black hole, the haunting possibility of life evolving on a world of slow-motion geology, or the terrifying psychological toll on a potential explorer? Share your thoughts and your biggest questions in the comments below. Let's keep this exploration of the cosmos going together. And if you're ready to dive into another mystery at the edge of reality, be sure to like this video and subscribe for more journeys into the unknown.